Okay, welcome everybody to today's episode of the California Dreams Technical Seminar Series. We are lucky today to have a recent speaker back. A few weeks ago, Rehan Kapadia talked about what we're doing in Moses 2.0, and as much effort and skill and expertise as he puts into Moses 2.0, Rehan also has his own research agenda, actually several agendas. And today he's going to give a talk about one of those several agendas. Rehan has been on the faculty in electrical and computer engineering at USC since 2014. He currently holds the Colleen and Roberto Padovani Early Career Chair and is newly minted director of Moses 2.0. He was the co-director until just recently. So we're very grateful for him taking on that responsibility. He's also the director of the John O'Brien Nanofabrication Laboratory at USC. He's got degrees from the University of Texas at Austin and UC Berkeley, and is the winner of many awards, including the AFOSR and ONR Young Investigator Awards, and the Peter Mark Memorial Award from the AVS, which I just learned today is the American Vacuum Society. So thank you, Rehan, for teaching me that today, and I hope to learn more in your upcoming seminar.
All right, that's a great transition, Steve. So thanks everyone for stopping by and listening. So today I'm gonna really be talking about some of the work that my group and myself have kind of done over the last decade or so, focused on trying to understand how we can improve the ability to grow high quality semiconductors, specifically 3-5 semiconductors, on substrates that you wouldn't normally grow them on, such as metals, oxides, silicon, kind of focusing on and thinking about how we can do something on the back end, but also with some work on front end integration. So before I kind of jump into that, my group does kind of have a broad research agenda, and this is one of the focuses. So we can think of it as kind of back end and front end material growth and heterogeneous integration, focusing on trying to understand the fundamental mechanisms of growth and thinking about how we can potentially come at it from a different aspect or a different angle to enable integration, heterogeneous integration, monolithically. So essentially, really, instead of having to take two wafers and bond them together, or take one material, lift it off and transfer it, how can we just directly grow the materials that we want to grow on top of each other? So that's what we'll talk about today. And I also have a pretty robust research agenda and research focus on using electronic devices and integrated photonics for electron emission devices, focused on trying to use device physics and semiconductor fabrication technologies to enable us to take signals that are on optical beams and convert them with high fidelity to an electron beam. There's a lot of interest in that because it allows you to get very significant amplification of signals, and that's very important, especially at the higher frequencies. And so that's a value for communications, radar, things like that, and then all the way through to electronic warfare and high power microwaves. And then finally, we have efforts focused on in-sensor computing and kind of novel computing approaches to dramatically reduce the energy consumption of what we're mainly focused on today are artificial intelligence algorithms, so things like neural networks and whatnot. So that's kind of the overall portfolio. Today we'll be talking about our work on materials growth specifically. And so to just jump into it directly, the key challenge with any monolithic materials growth approach, where you take a substrate and then you try to directly, atom by atom, grow another material on top of it, is that essentially what ends up happening is that you have to be able to match the lattice structure of the material that you're trying to grow with the material you're growing it on. And so what that typically means is you have to grow the same material on the same material, or you have to be lucky that the exact crystal structures match very well. And so we have been working on a few different approaches to try to address this specific challenge and attack this specific challenge. And I'll go through each of these in the talk from left to right, where we talk about how we can kind of break some of the fundamental trade-offs that you run into when you're trying to grow, say, a crystalline material like a 3,5, like indium phosphide, on something that doesn't have any epitaxial registry with the material you're growing. So meaning, there's no crystal structure from the substrate that you can use to imprint the material that you're growing. So for example, I'll talk about how we grow 3,5s on metal foils or metals. And then we'll expand that to talk about how we can grow 3,5s on oxides. And then finally, I'll talk about some of our very recent and in fact unpublished work on 3,5s on silicon. So to kind of go back to that point that I was making earlier, it's very important to be able to integrate different types of materials together, and it's becoming more and more important. This is heavily driven by the fact that if you can have two different materials which enable two different technological capabilities, you typically want to be able to have the highest communication bandwidth between these different materials or different blocks, different logical functions. And in the end, for anything that's on a chip and driven by electrical signals, the distance between two things is kind of fundamentally ends up limiting your bandwidth between those two things. And this is why everybody wants to do stacked materials. This is why we have high bandwidth memory. This is why if you look at the future of NAND flash, people are trying to put the silicon circuitry underneath, put the layers of NAND flash on top. I mean, this is just basically the direction that everyone is trying to go for everything, because if you can put more stuff closer together, yes, you generate more heat, but you can send signals back and forth between different parts of your system with much, much higher bandwidth. And as we know from kind of all of the work on AI and computing, that is sort of the name of the game these days. So if we go back to then the fundamentals of this, saying, okay, well, why can't we just stack everything up and grow everything up atom by atom from one substrate? And it really comes down to the fact that, okay, well, if I have a substrate, say silicon or say indium arsenide or indium phosphide, then what ends up happening is the only materials that you can grow with high quality on top of them are materials that have this epitaxial lattice matching, so what we would call homoepitaxial growth. And so if you look on the left-hand side, we show an example where you start with the gallium arsenide substrate and basically make sure that all of the materials grown on top of it, even though they're not exactly the same material, have very little strain, and so they don't end up generating defects. And this gives you your highest quality materials and your highest quality ultimately devices. The problem is that for a lot of materials, you don't have a good substrate on which to grow on. So for example, a lot of times we want to grow materials on a silicon substrate, but only a small number of materials really lattice match well to silicon. And most of the materials that we're interested in integrating with them, it does not, in fact, integrate lattice match to silicon. And so you end up with many more defects, and there's just a lot of tricks you have to play to try to get good quality materials. Finally, if we want to, for example, grow, say, a large area material for, say, a solar cell, or maybe some kind of other applications where you want to put a tunable material on a large surface, or you even want to be able to integrate materials such as 3,5s directly into the back end of line of silicon, well, then you don't have any crystal structure on which to grow on. You're going to be growing on oxides. You're going to be growing on, nanocrystalline metals. And so in that case, what you end up with is what we would call polycrystalline thin films, where essentially everything is just kind of randomly oriented grains that meet together. And so you get all these defects and you just have dramatically lower quality of materials. And I'll show an example of that later. So what we tried to do, and this is really what I was trying to do when I was starting out as a grad student, is I was kind of asking myself, well, is there a way for us to maybe improve the quality of the materials you get on these non-epitaxial substrates by being able to grow large area polycrystalline films, or large grain polycrystalline films, or even single crystalline materials. And the way that we kind of came up to do this back then, and so this was work that we did to try to understand solar cells and try to address the solar cell market, was, well, okay, if we can take molybdenum foil, and instead of using the standard metal organic chemical vapor deposition where we throw a gaseous precursor of indium down and a gaseous precursor of phosphorus down, and then grow things atom by atom, what if instead we split it up into two parts where I put a layer of indium on the substrate, I cap it with something, in this case silicon dioxide, I turn it into a liquid and make sure that the capping layer doesn't just controls it so that the liquid stays in the geometry that I put it in originally. And then I do a phase transformation, right? So essentially, just like if I take water and I start adding salt to it, and I keep adding salt to it, I stir it, the salt dissolves, I stir it, the salt dissolves. Eventually, you keep adding salt to the water, what happens is that the salt will crystallize out, and you super saturated it. I mean, we all know this intuitively, although probably with sugar, not with salt. But that's kind of what we do here, is where we take the substrate, we form a layer of indium, we turn it into a liquid, and then we supersaturate it, not with salt, but with phosphorus. And it turns out, if you look at the phase diagram, the only thing that can happen when you do that is indium phosphide will precipitate out. And so that's what happens. And so we enable that precipitation of indium phosphide, and then what we do is we control the actual grain size, and we control the actual quality of that material by tuning the conditions. So that includes flux, that includes temperature. But the key thing here is that what it allowed us to do, and this was back in 2013, so 12 years ago when we published it, and I think the first time we saw this was in 2012 sometime. So what it allowed us to do was actually show that if I could take a substrate which had no epitaxial relationship with the material that I was growing on top of it, and actually grow really, really large crystals on top of it. And that was something that was quite unique at the time, because that had not been seen before. So it turns out that what you get is these materials where you have hundreds of microns of grains that have twins in them. And so what that means is, if I look at the mobility or the electron concentration, what it kind of means is that you can actually get to qualities of materials where you have, say, a mobility of this indium phosphide on a substrate of around 500, which is not put into context yet, but it will be later, because almost all polycrystalline materials, like these 3,5s that you could grow at the time, if you took a metal substrate and you grew those materials on top of it, you would end up with mobilities on the order of, say, 10 to 20. So essentially what this showed us is that, hey, there might be a route where we can dramatically increase the quality of materials that we grow on these non-traditional substrates, at least for the 3,5s. So that was kind of the starting point here. And there's other kind of metrics and measurements that we can show to show that these have relatively good quality. But kind of the key thing here is to say that, okay, well, before this approach, what you really were stuck with when you were growing these polycrystalline films on non-epitaxial substrates was materials that gave you mobilities on the order of, say, 10, 20. And now we could potentially extend it up to about 500 or so. So that's much less than, say, a epitaxial single crystal, epitaxially grown single crystal layer, but it's dramatically higher than anything else that you could have done on a non-epitaxial substrate. So it started to make us question, okay, well, what else could we do? And so one of the approaches that you can use to measure the quality of a material is something called the luminescence efficiency, where you take a material, you carry out photoluminescence, where you shine light on it, and then you measure the intensity of the emitted photons. That, if properly done, can be calibrated so that you actually understand the quasi-Fermi level splitting between the electron and hole quasi-Fermi levels. And what that kind of tells you is it's a proxy of quality. And so essentially what we were showing here is that if you did that, you got some pretty high quality materials that suggested that we could potentially make good quality solar cells out of it. And that was in fact what we did. So this was basically a polycrystalline indium film grown, indium phosphide film grown on a molybdenum surface, and we showed that you could actually start to approach the quality of a single crystalline indium phosphide waveform. So that was something that was very interesting and kind of exciting. But these really kind of belied what what is going on underneath, and that's really the question that we were asking ourselves. And says, okay, well, what's actually happening, and then is there a way for us to take advantage of that to do more interesting stuff? Because in 2013, new materials for solar panels were interesting. That was interesting back then. But as time moved on, it was kind of clear that silicon was a big winner and was going to continue to be a big winner. And then you would probably also have some CAD/TEL from, say, First Solar. So that we started to ask ourselves, what are the fundamental mechanisms behind this, and what are the next things that we can do? And so the way to kind of think about how standard vapor phase growth works is that you have some material you want to grow on. So that's your substrate. That material has either some, it's either single crystalline, it's polycrystalline, or it's amorphous. Depending on that, it will tell you what kind of materials you can put on top of that material, on top of that substrate. And so if you wanted to do anything on, say, metals or oxides, you basically end up with materials that kind of look like what I'm showing over here. So these are both indium phosphide grown on metals. So on the left-hand side, it's actually indium phosphide grown on a molybdenum foil using a technique called close space sublimation, which is kind of like an evaporation technique. One of the typical ways that people have grown CAD/TEL, CAD sulfide solar cells. And then on the right-hand side, it's a metal organic chemical vapor deposition. So kind of the state-of-the-art 3-5 growth technique that we use for almost everything on a sputtered molybdenum layer on a silicon substrate. But the substrate that it was growing on was molybdenum, so nanocrystalline material. And so the key thing to understand from both of these is that there's kind of this normal trade-off that happens when you make these types of films on non-epitaxial surfaces. And that trade-off is fundamentally that when you start to grow, you get a bunch of nuclei that form on the film. And these nuclei come from the vapor phase precursors that are coming down, hitting the surface, moving around, joining together, and then growing. The orientation, the crystal orientation of these different nuclei is not controlled. And because it's not controlled, each one kind of has a different orientation. And so what happens is you get these different orientations, they grow, and then they meet and you get a film. Now, of course, what you could do is you could say, oh, well, why don't I just make these nuclei really far apart? That would be great. But the problem is that you don't have control over the directions in which you're growing. So because you don't have control over the crystal orientation of each of these various nuclei, you don't, in general, have any control over the difference in the growth rate vertically versus laterally. And so what you end up with is this kind of rule of thumb, which is if your lateral grain size is, say, n, your height is going to be on the order of half an n typically. So that means that if I want grains that are 2 microns in 2 microns in lateral dimension, I'm going to need probably at least a micron or so height. If I want, say, 20 micron grains, I'm going to need 10 microns of height. And if I want something that's, device scale 50, 60 microns, then it starts to end up being film thicknesses which are just not useful. So it's basically like you're growing a bulk material. So this is kind of the traditional approach in vapor solid growth, and this is how it works. And what we do here is a little different, where we take a substrate, we put a liquid layer down on that substrate, and we don't put it down as a liquid. We evaporate indium, we heat it up, it turns into a liquid. And then what ends up happening is that by tuning the flux, the temperature of the substrate, as well as the flux of the group 5 precursor into that liquid indium, you can actually tune the spacing between the nuclei. The thing is, though, that what ends up happening is here, because the growth can only happen in this encapsulated layer, you can basically choose the thickness of your film and then tune the growth conditions so you choose the grain size, the lateral grain size. And so essentially what that allows you to do is it allows you to have relatively large grains here. So for example, in this case, we're showing a growth where the indium phosphide nuclei are on the order of a few microns apart. I'm sorry, not a few microns, on the order of millimeters apart. And then these are each grain is grown dendritically, and there's a very fundamental reason for that. I won't get into it, but it has to do with the rate of arrival of atoms at the surface of a growing crystal, as well as the speed at which an atom on a surface moves to find the lowest energy configuration of that crystal. And so what ends up happening is that we can do this. We can get these really nice, relatively large grain polycrystalline materials, and then you could actually go in and we can do a simplified model. So this is a simplified model that borrows from the math and the physics of how we typically approach, for example, submonolayer epitaxy, where you look at a surface, you're sending atoms in at the surface, and you do a simulation by essentially tracking the populations of all of the different types of cluster sizes. So a cluster size of a single atom on a surface, cluster size of 2 atoms on a surface, 3 atoms, 4 atoms, 5 atoms. So you just make a big, you make a big set of differential equations, and you just solve that. And so that is one approach. So we took this and we simplified it. And basically from there, what we were able to show is that you could actually control the nucleation density in a film like this across a pretty large range, just by tuning the flux of the group 5 precursor that goes in there. And so the reason that's important is that it kind of tells you, hey, now we have kind of a new knob to tune the crystallinity and reduce the defect density of these materials on non-epitaxial substrates. And there's some theoretical underpinning to that, as well as some experimental data that supports that. Now the question is, okay, well, that's nice, but polycrystalline materials are, they're fine for maybe solar cells, but for most other applications, we don't want that. We want to actually move to single crystal. So what can we do? Well, if I look at this, I can say, oh, well, if you just ignore all the parts around it, it's a single crystal. So then, okay, well, why don't we actually just do that? Why don't we take this, and why don't we take a substrate, and instead of depositing a film, a layer of indium, why don't we just pattern it into just the geometry of the devices that we want? So this is an example on the left-hand side where we carry out this growth on a silicon dioxide surface with a thin layer of molybdenum oxide on there. And on the right-hand side, we do something similar, but without molybdenum oxide on there. And so what ends up happening is that we found that, okay, well, it turns out that the actual control over the substrate liquid surface energies and the liquid capping surface energies turns out to be critical here. And so there maybe are some limitations to kind of what substrates you can do this on, not driven by your traditional epitaxial relationship, but maybe driven by your surface energy constraints. Now, ultimately, we figured out how to get around those, and I think I have a slide on that. But what I'll do is I'll talk about how we then essentially took this polycrystalline growth approach and turned it into a single crystalline growth approach. basically by, instead of using continuous films of a material, we actually used a mesa. And so this shows circular mesas where you start off with some substrate, you have an indium layer, indium, indium mesa, and then silicon dioxide capping layer. You essentially take it, you heat it up, the indium turns into a liquid, stays where it is, you expose it to a group 5, such as phosphorus. The phosphorus will decompose either in the chamber or on the surface. It'll supersaturate the indium. You'll form nuclei. Those nuclei will grow out, and then you'll get a crystal. And so the top is a cartoon. I mean, I think that's probably obvious to everybody. It's a cartoon. But the bottom is actually a set of SEMs showing how crystals actually grow in these, whatever you want to call them, micro reactors, micro templates. Essentially, what happens is that you start off and you expose it to phosphorus. It nucleates. It starts to grow an initial indium phosphide crystal. That crystal will continue to grow. These are from different growths. This is not just an in situ image, because that would have been very challenging to get. So it's growths for different times, and it's showing how the crystals grow, where it basically starts off and it grows, and then consumes the entire template. So essentially, you get the single crystal, and you get it in the geometry that you want on the substrate. Now, it does turn out that how you control this brings in a new constraint that we don't typically deal with when it comes to 3-5 growth, which is this liquid metal wetting on the surface. So there's a reasonable amount of material science behind this, but fundamentally, what all of the stuff on this slide tells us is that if you have a substrate and you want to do this type of growth, what you need to do is you need to be able to control the ratio of the height to the diameter of the substrate. And diameter, because it's a circle, but it doesn't have to be a diameter. Really, it can be a line, it can be something like that. So there, depending on the surface energies, you end up with a kind of diameter to height or line width to height kind of constraint. And if you don't follow that constraint, what ends up happening is that you can end up getting de-wetting. But the moral of the story here is that we have a good thermodynamics-based model, surface energy-based model, where we, for example, over here, we kind of show the black line is our model for how we expect things to happen. And then all of these dots are de-wetting tests on different substrates. And so kind of moral of the story there is that we sort of think we understand it. And again, we have a basic material model that is not calibrated, but that is that matches with experimentation. And so we kind of have a reasonable understanding of the material science of what's happening there. And the takeaway is that depending on what you want to do, there's basically some geometric constraints, but as long as you can follow those geometric constraints, you'll be able to kind of use this approach to grow on any substrate that's inert to what you're growing. So then you can go ahead and you can do optoelectronic characterization of these materials. What we're showing here is just some kind of comparison between what we're growing on and what just a straightforward indium phosphide wafer looks like. And so that's what we think is the correct comparison here, because it's really like we're growing a bulk substrate. So these are kind of on the order typically of hundreds of nanometers to maybe a micron thick. And so we kind of show that there's similar-ish behavior. It's not exactly the same, though the single crystal wafer is better, but it's definitely quite similar, and it's something that is not possible without by using a standard vapor phase technique. It's just you just can't do that. We also looked at alloys like indium gallium phosphide, and we found some really interesting results here. So what we ended up finding is that you could actually tune the fraction of gallium and indium, and you could get a material where you had an indium gallium phosphide alloy. And while that's something that's pretty straightforward to do when you're in a vapor phase, and even when people did liquid phase epitaxy way back in the day, it is actually should not work in this scenario, in this case, because what ends up happening is if you want to be able to grow a crystal with a uniform composition, you then need the mole fraction of, say, indium and gallium in the liquid to equal the mole fraction of indium and gallium in the solid material. And if you look at the thermodynamics, if you look at the phase diagrams, that doesn't actually happen. So we did this experiment because we were fully expecting to get graded materials where we had gallium phosphide on one side and indium phosphide on the other side. And we actually found that that was not the case. And what we realized is that essentially, if we were able to push the growth fast enough, we were able to move away from that thermodynamic limit, and we were able to be a little bit more kinetically driven, and that then allowed us to get compositions in the solid that were closer to the compositions in the liquid, instead of what what we would expect from a fundamental thermodynamic analysis. And so then we said, okay, well, if we can do something like this, what happens if we mix two crazy materials together that you wouldn't expect to have a good quality interface? And so, one of the cool examples that we have is we took a indium and tin mixture where there's no such thing as indium tin phosphide. There's just doped indium phosphide and there's tin phosphide. So there's no alloy component that exists, so no alloy can form. It's forbidden. What you actually get, and something that we found really interesting, is you get this lateral heterostructure between two materials that have totally separate crystal structures. So this is kind of an interface where you have a reasonably sharp interface here. It's almost atomically sharp. I wouldn't say exactly. Maybe there's a couple layers between them. But it's almost atomically sharp interface between two materials that have crystal structures that are totally different. And that is not something that you would traditionally be able to do if we just took a vapor phase growth technique, and we put that on top of, and say we had an indium phosphide substrate and we tried to grow tin phosphide. We wouldn't really be able to get these high quality interfaces except for very, very small areas. And that's because the tin phosphide just wouldn't nucleate the way that you want it to nucleate. It wouldn't be single crystalline because there's nothing to guide it. There's nothing to guide the atoms as they come down. And so this was really interesting to us because what it told us is that, well, the way that this works is that when we take a template, we put indium in there, we put tin in there, we expose it to phosphorus, what ends up happening is that because of the thermodynamics of indium phosphide precipitating versus the thermodynamics of tin phosphide precipitating, indium phosphide precipitates out first. And so what ends up happening is you just grow half of your template into an indium phosphide crystal, and then you're just left with a bunch of tin. Then what happens is that the phosphorus keeps coming in, and then you grow tin phosphide. Now, the thing is, the tin phosphide doesn't nucleate off the indium phosphide. It nucleates somewhere else, and then it just grows, and the two crystals kind of just meet. Instead of, they just meet and they form this interface instead of what you would normally do when you're growing vertically, where, you start with one fully formed crystal and you come in and add an atom at a time. And so any strain issues, which are the key thing, which kind of causes big problems in this area, they kind of get mitigated because you're forming the crystal separately. And so then they kind of almost zipper together, but they zipper together in kind of a different way than you would normally expect. And so that's something that was very unexpected for us, and it's something that will come back to when I'm talking about the heteroepitaxial growth. But at this time, one of the questions that we had, so this was, this was published in 2018, and this was kind of work done in 2017. And about that time, everyone was starting to think about, okay, well, what about back end of the line integration? And there's many rules for back end of the line integration, but there's really one rule for back end of the line integration, and that's you have to maintain your thermal budget. The exact thermal budget will vary from CMOS technology to CMOS technology, but in general, the rule of thumb is, okay, we need to be below 400 degrees C, and if we're below 400 degrees C, we're probably not going to cause any significant damage to, say, the gate stack or the silicides, or which are for the contacts. We're not going to do any kind of irreparable damage. That's the typical rule of thumb. So then that was our question. We said, okay, well, can we do that? And so the first thing that we did is we said, okay, well, let's just take this growth, and we'd always done it kind of between 450 and say 800 before, and we said, okay, let's see what happens as we drop the temperature down. And so what we would do is we did a growth study where we looked at the growth at 550, at 350, and 300, and then we just used photoluminescence, where we just looked at the intensity of the emitted light when we would shine a laser on it, and then look at the spectrum of that as a proxy for quality. And so essentially what we would say is that, okay, well, we want our, very simply, you want your kind of your photoluminescence to have the right peak position, and you want it to have the smallest line width possible. So the peak position matters and the line width matters. And there's a reference, which is an indium phosphide wafer, which kind of is like, okay, well, that's a single crystal. That's kind of the baseline reference. And so what we see is that actually when you drop the temperature down, you get this, you actually get this drop in quality, and then it goes back up. This drop in quality is accompanied by a shift in the peak position because of essentially extrinsic dopants. So it's incorporation of point defects that end up doping the material. And this comes from the Bernstein-Moss shift that happens in semiconductors when you have very heavy doping, degenerate doping. And that's what causes both the peak position shift as well as the full width half maximum expansion. And so what we see is that actually there is a low temperature regime in which we get material that might actually be good. And so we did this study, and we actually saw that, with respect to all of the kind of key metrics in photoluminescence, the peak position, the full width half maximum, and something called the Urbach parameter, which is it kind of tells you about how the conduction band and valence band tail into the band gap, and it's kind of a measure of disorder. So a higher Urbach parameter tells you that you have more disorder, it's worse. And that's exactly kind of what we saw here, is that, at higher temperatures, we got something that was similar to the indium phosphide wafer, and then actually at lower temperatures, you got, so then it went up, and then it dropped back down, and then if you went to too low of a temperature, then it just got ridiculous as well, and that's because then you're at such a low temperature that you're not getting the growth that you think you're getting. So what we found is that there's this interesting kind of window on the order of about 300 C where you can start to get good quality material. And so that was for indium phosphide. So then we said, all right, well, what about indium arsenide? Indium arsenide is a high mobility material. Can we grow it on a single crystal? I mean, can we grow it on a non-epitaxial substrate, such as silicon dioxide, and then measure the mobility and kind of see what we get out of it? And so this is just some pictures showing that, we in fact did that. We turned it into a Hall bar. So we made a cross of indium arsenide, thin film indium arsenide grown on a silicon dioxide substrate. And then what we did is we actually measured the mobility as a function of temperature, and we found that at room temperature you could get electron mobilities on the order of about 6,000 or so for indium arsenide. So I'll put that into context in a second. It's definitely still considerably lower than, for example, the type of mobilities that you would get if you were growing on a pure single crystalline material, which are still much higher. However, what we kind of showed is that this mobility is probably limited by the surface roughness. And so even though we're at 6,000 right now, we should probably be able to get to about 20,000 or so, which is a pretty good mobility for something that would be grown on a non-epitaxial substrate. And so that's work we did in the past. And the key thing to put it into perspective is if you look at what we kind of showed over there, both through our indium phosphide work as well as our indium arsenide work, on a log scale. If you look at the quality of the material as using electron mobility as a proxy, as compared to basically any other approach that you can find in the literature, you can see that there's essentially it's kind of a line. Here's what vapor phase polycrystalline indium arsenide gives you, something like 200 centimeters squared per volt second, and this is what we're experimentally observing, which is on the order of 6,000 or so. So we're getting almost like a 10x increase in quality compared to any other approach for any other material here. But the thing is that if you look at a single crystal epitaxial material, it's still up here. So we're much higher than any other approach, but there's still a ways to go if we want to make the highest quality materials possible on these non-epitaxial substrates. And so there's still stuff that we don't understand. That's the kind of the takeaway there. So then the question becomes, okay, if this is what we get when we do this on a non-epitaxial substrate, what happens if we do this on a heteroepitaxial substrate, right? What if we take this and we grow this on silicon? And so I didn't put a big set of slides in here describing the traditional state of the art for heteroepitaxy on silicon, but fundamentally, the approach that people use is to create some kind of buffer layer, and that buffer layer can be composed in different ways. And the whole job of that buffer layer is to essentially take all of the defects that get formed when you create a, say, a 3-5 silicon interface and somehow recombine them or bend them or prevent them from propagating all the way up. And then you grow a high quality layer at the top of that. And typically, even though you can do a lot of work, the quality of those materials has still traditionally not gotten to the point that it's been especially for I'm talking about for thin films right now. Talking about for thin films, where it has necessarily yet been commercially viable. So that's one of the key things and key challenges that people have tried to work on. There has been huge amounts of work on this over a long period of time. So we said, all right, well, let's look at this kind of differently. So what we did is we said, all right, well, we have MOCVDs too, so let's use that. And so we took silicon and we just, in a naive way, meaning not thinking about defect filtering or any way, just grew a layer of indium phosphide on top of that. And then we said, well, let's do homoepitaxial growth of indium phosphide, of TLP indium phosphide, templated liquid phase growth, this liquid phase approach. Let's do homoepitaxy of that indium phosphide on top of our defective MOCVD-based indium phosphide. And so this is kind of the way that we would do it. We take a silicon wafer, we do a layer of 3/5 by MOCVD. We'd do our indium evaporation, we cap it, and then we'd grow, say, indium phosphide or indium arsenide or some material in there. I'm mainly talking about indium phosphide, but in general, all of the binary 3/5s are fairly straightforward to do. And so then this kind of shows the surface, but the key thing that I really want to point out here is that on the right hand side, I'm showing a TEM, so transmission electron microscope image, where we have your silicon substrate down here. Then this is the MOCVD layer that we've grown, and then this is the templated liquid phase layer that we've grown. Now, the key thing to keep in mind is that for when you see these lines here, any kind of line or zigzag or these all of these sharp lines, they are defects. And so what you can see is that there's a huge amount of defects in this underlying material, which is exactly what we would expect. What we did not expect is that if you look at the interface between these two, the defects don't seem to propagate through, and that's something that is quite unexpected. It's not something that we would have anticipated when we initially did this for multiple reasons. And there's multiple reasons behind that, but let's just focus on this. So basically, we said, okay, well, that seems cool. How much are we filtering out? How much of the defect density are we filtering out here? And so what we did, and so this was done by my student in collaboration with another faculty's postdoc at USC, and we're in the process of writing up this paper. But essentially, what we did is we said, all right, let's take our wafers where we have silicon, and then we have our MOCVD indium phosphide layer, so the poor quality one, and then our TLP indium phosphide layer, which seems to be higher quality. And let's actually go through and do plan view TEM. So we actually take the sample and we basically shave it off so that we can see a slice of the underlying substrate, and we can see a slice of the TLP grown material. And so what you see here is when you actually take those slices, is that there is just extraordinarily high defect density in this underlying layer. And then when you go to the material that we're growing on top of them, you're getting maybe 100x, potentially 1000x reduction in defects just by having one single interface. And that is something that is extremely unexpected. It's extremely unexpected. We wouldn't have we would not have expected that. But in fact, it does happen. And this is a very compelling proof, because essentially what we're doing is we're showing as much of the mesa as we can. So, we grew like a 10 by 10 mesa, and this is showing, or maybe I think this was maybe a 20 by 20 mesa. And then we're showing, about 5 microns by 10 microns of it, which is limited just by the fact that it's extremely hard to do these kind of plan view TEM cuts and then imaging. And so it took a lot of skill and expertise. And in fact, this was something that I had sent out to a professional company to do, and they failed multiple times, and we finally just ended up sucking it up and doing it in-house. So this was something that was super interesting. And so then what we can say is that, all right, well, let's try to figure out, get some perspective on the improvement in quality. And so one of the things that we could do is we could actually take a photoluminescence map of the grown indium phosphide. So this templated liquid phase indium phosphide that's grown on top of the MOCVD indium phosphide. And we could look at the intensity, because intensity is a proxy for quality. And what we see is that we get something like typically 100 to 1000x improvement between the underlying MOCVD-based 3.5 that I grew and the TLP-based 3.5 that I grew on top of the bad MOCVD 3.5. And that relative difference kind of corresponds, it kind of makes sense based on the counting that we can do when we do plan view TEM, so it's consistent. However, it's still not perfect, and this is one of the things that we can see here is that, what I would have expected if we had this as bulk is I would have expected the mobility to be on the order of around 3000-ish. But here our mobility is, on the order of about, say, 1600-ish. And so we're still about 2x lower than we would like to be. But essentially, this is a very promising and interesting result. And so one of the kind of cool measurements that has been done on this is that this is nano XRD. So essentially where we take a nanoscale X-ray beam and we use that to very, very locally probe the properties of the material. And so what we can do from there is we can actually look at the full width half maximum of the reflected beam from due to our crystal lattices. And essentially, if you have a perfect crystal lattice, then when you have a reflection in an X-ray system, that will have 0 width. And then what happens is, because you have imperfections and you have strain and you have defects, and that causes strain, that essentially will broaden out those peaks. And so essentially, the higher the peak, the worse the quality. This is just kind of a heuristic that you can use here. I wouldn't say that's exactly true, but that's about what's true. And so what ends up happening is that you can see this blue line over here is what you get from just a single crystalline wafer. This light blue line is what you get from templated liquid phase indium phosphide grown on a single crystalline wafer. So you can see that basically, the quality is just as good as you would expect, because it's homoepitaxially grown on a single crystalline wafer. And then here is what you actually see from the MOCVD indium phosphide. So you can see that there's just a massive range of full width half maximums, and that's just because there's such a large density of defects there that you get all kinds of broadening depending on which exact spot you look at. And then this is the TLP indium phosphide that's grown on top of this layer. And so you can see a very nice visual demonstration of how we've dramatically reduced that defect density here. And I think that's something that's quite interesting and unique. Now, I'm running out of time, so what I'll do is I'll just skip slides, and I'll go to the end. And basically what we've done kind of over the past 10 years is kind of look at, all right, how do we try to enable monolithic integration of these 3.5s using approaches that are different than the standard MOCVD based approach. And what we've kind of been circling is this idea of, instead of bringing in all of your atoms and your precursors at the same time, what you can do is you can split it up into this liquid phase based approach where I split it up and I use the group 3 first, and then I introduce the group 5, and that just gives you these new dimensions and new of control. And so then that's what gets us these very interesting, in my opinion, interesting results. And so with that, I'll go to the last slide. And yeah, I mean, I have a lot of great PhD students over the years. A lot of this work was done by Dr. Sarkar, who is a researcher at IBM, as well as Jun, who is a engineer at NVIDIA, as well as Hyun, who is an engineer at Intel. And then I also had some work from a couple of the postdocs who worked for my group, who are at Amazon and at a university in India. And so my research has been funded in general by a number of different organizations, including NSF, the Air Force, DOE, JPL, Semiconductor Research Corporation, and then USC put a good amount of resources into our growth lab. So I always acknowledge them as well. And so that's, yep. And so that's my talk. Happy to answer any questions.
Thank you very much, Rehan. There are 2 questions in the chat window. The people who ask those in the chat window are welcome to come off mute, or if you prefer not to or don't have a working microphone, we can read the questions.
Yeah.
Sachin, do you want to state your question? It's from a while back, so maybe you can give us some
Okay.
context.
Yeah, sure. Can you hear me, guys?
Yes.
This is Sachin. Hey, Ryan, great talk. I wanted to ask about the CAD telluride. Was it a vapor deposition process? What's the growth rate on it, and what's the maximum thickness you have achieved?
Yeah, so that one is a closed space sublimation tool. And so that was done back at Berkeley, actually, when I was there. So there's a grad student. And essentially the way that a closed space sublimation tool is that, and it's very specific for CAD-TEL, because when you evaporate CAD-TEL, it has this unique property that cadmium and tellurium kind of come off at the same rate, which is not true for literally any other compound semiconductor. I don't know if it's not true for literally any, but basically none others. So that's unique. And so it allows you to do this closed space sublimation where you take a substrate, you heat it up, and then you put your target really close to it. You heat up your target, you basically do evaporation onto your hot substrate, and then you grow these crystals. Typically for that, it's been used for solar cells, so it's typically been limited to on the order of like 10-ish microns. See, I think you're asking from an X-ray perspective, right? X-ray detection perspective. And so for there, you're probably looking for like hundreds of microns to millimeters, in which case I wouldn't say that this is the right approach to that, because you're kind of going to end up being limited. And I don't know if I assumed correctly, but that's my assumption. All right, I'm just going to assume that I assumed correctly and pat myself back and move on.
I always assume that you're right.
That's right. So there's another question. Can the background doping of the indium phosphide be measured? Yes. So typically we get on the order of maybe about 10 to the 15 to 10 to the 16. And that actually is, we use an electron beam evaporated silicon dioxide layer. So what happens is when you do an electron beam evaporation of silicon dioxide, you actually get substoichiometric silicon dioxide, which is SiOX, so it's not really SiO2. And the thing about the material SiOX is if you take SiOX and you heat it up, it actually will do something where it breaks apart and you get silicon and SiO2. And so what ends up happening is that where X, so SiOX, where X is less than 2, I should say. And so what ends up happening is you can get a source of silicon doping if you just use a silicon capping layer. And that's where we see this, this background doping concentration from. And that's actually the reason for that temperature dependence that I showed as well. So it can be reduced to lower if you control the capping layer and you modify that. However, the doping level can be controlled in two ways, both for p-type and n-type materials. So for one way that you can do that is you can actually co-evaporate a really thin layer of some dopant. That was actually the genesis of that tin work, where we were co-evaporating a very thin layer of tin on top of the indium. And what ends up happening is you can control that, and when you control that, you actually can just do liquid phase doping with the material. The second thing that you can do is you can actually co-flow a dopant precursor. And so say I want to make it p-type, I can co-flow diethyl zinc in there. That will introduce zinc into the material as it's growing, and that'll make it p-type. And so we actually have a paper where we've shown p-type material, indium phosphide, grown exactly that way. And then the last question was, so what are those interface? What are these things right at the interface? And the really interesting thing here is that I'm pretty sure that these are the very, very tiny voids at the interface between the indium phosphide and the MOCVD indium phosphide and the TLP. And we can actually show that, we've actually shown that through some other approaches where there are these small voids that form at the interface. The origin of those voids is most likely, let me clear all these rings. We pretty sure, we believe it's coming from the physics of what happens here. So I didn't talk about this before, but fundamentally, the mechanism of de-wetting of a liquid film here it's actually a nucleation and growth problem. It's just that what you're nucleating and growing is a void. And so that's kind of the physics of what we're calculating here, which is, what is the free energy change of a template without a void versus with a void as a function of this void radius. And what you see is that, and just for everybody, if in this case, if the free energy change is above zero, it means it's not thermodynamically favorable. If it's below zero, it means that, okay, well, there's a lower energy state my system can drop into, and so it will try to do that. And that's the basis of our model, and that's what we see here. But essentially, what we also think is happening, and this is true for any material, any nucleation and growth, this is anytime there's a nucleation and growth event happening, is that you also have these what would be called subcritical voids, where essentially you're creating nuclei and they're disappearing, they're creating and they're being created and they're disappearing. And we think that's actually what's happening in these materials because they don't de-wet, but what's happening is you're probably still creating and eliminating voids over time. And when it's in liquid phase, that's fine because those voids are being created and eliminated, created and eliminated. But then once that indium turns into solid indium phosphide, those voids, however they were at the time, they just stay frozen there. And that's exactly what we think we're seeing.
Thank you. Amy, do you want to put the slides up on future seminars? We can still take any more questions that anybody wants to unmute for while we put those slides up. Are there any further questions? If not, let's thank our speaker one more time. Thanks very much for the illuminating seminar, the great talk, Rehan. And thanks for all your contributions. Here's the schedule of upcoming talks. There must be a mistake here because we don't see Rehan speaking again within the next couple of weeks, but we'll get that fixed. But we have a great lineup of speakers here with GP Lee coming next week from UC Irvine, Austin Minnick from Caltech, and you can read the rest, but we're very grateful. And kind of a special seminar on August 15th on workforce development, position analysis methodology. I think is the best way I could say that. So we'll look forward to Andrea Belz's talk on August 15th. So,
right. Thanks everyone.
Yep. Thank you, everybody.
Bye-bye.